Today in this section we are going to discuss about partial order sets and partial order relations and lattices. So we start with the definition of partial order relation. A relation on a set is called a partial order relation if the relation is reflexive, antisymmetric, and transitive. By the time antisymmetric, what we mean is if uh, x is related to y and y is related to x, then x is equal to y. So here, uh, if r is a reflexive relation, then x is related to x itself. If r is an antisymmetric relation, then x related to y and y related to x implies x equal to y, and r is transitive, that is x related to y and y related to z implies x related to z. So if a relation has all these three properties, then that kind of a relation is known as a partial order relation. A non-empty set on which a partial order relation is defined is known as a partially ordered set or POSET. Now, let us have some examples of partially ordered sets. The first one, the set of all real numbers together with the less than or equal to identity. So R, set of all real numbers together with the less than or equal to identity. So if you take a real number x from R, then x is less than or equal to x itself. That's reflexive. Then second one, if we take two real numbers x and y, then x less than or equal to y and y less than or equal to x implies x is equal to y. And the third case, x less than or equal to y and y less than or equal to z implies x less than or equal to z for any three real numbers x, y and z taken from the set of all real numbers. So it has all the three properties, and therefore R together with less than or equal to identity is a partially ordered set. Now, the second type of second example is the divisibility relation defined on the set of all positive integers. So let us consider the set of all positive integers, which is usually denoted by z plus, and consider the divisibility relation defined on it. That is, we say that A divides B if B is the multiple of A or integer multiple of A. For example, we can say that 2 divides 4 or 3 divides 6, and it's obvious that 2 does not divide 7. So that is how the divides relation works. And if you if we define the divides relation on the set of all positive integers, then it will work as a partial order relation. For example, or for to prove this, if you take two integers, say a and b, then okay, first case, a divides a, since a is equal to 1 into a. A is an integer multiple of a itself, so a divides a, so that's a reflexive property. And second one, if a divides b and b divides a, that is a is equal to some n into uh, b is equal to some n into a, and a is equal to some m into b, and this happens only when a is equal to b. And the third case, if a divides b and b divides c, then a is equal to some okay, b is equal to some n into a, and c is equal to some m into uh, b, and that implies c is equal to m into b is replaced with n into a, so it is n into m into a. So c is an integer multiple of a, and that means a divides c. So it has all the three properties like reflexive property, antisymmetric property, and transitive property, and therefore divides is again an example of a partial order relation, and Z plus together with divides as a partially ordered set. And now if we consider the power set of S, the power set of S where S is a non-empty set will also form a partial order set under the relation of the inclusion relation or subset of relation defined on the set of all subsets of a set. So let's consider a non-empty set capital S. Capital S be a non-empty set, and P of S be the power set of S. And on the power set of S, that is the collection of all subset of S, we define the subset of relation. Now, obviously, if we take an element A, B, and C, three well elements in the power set of S, then if you say if you take an element from the power set of S, then A is a subset of A itself, that's reflexive. Second property, A subset of B and B subset of A means A equal to B. And the third property, if A is a subset of B and B is a subset of C, then A is a subset of C. So if you have all these three properties, then the given set P of S, power set of S together with subset of relation become a partially ordered set, or in short, POSET. So these three are three important relations or important examples of a partially ordered set. Now, if we take some subsets of a partially ordered set, then the partial order relation defined can be restricted to the subset, and that become uh, a partially ordered set. So, for example, if we consider instead of considering the set of all integers, if we consider the set of all divisors of a number like say 45. If you consider the set of all divisors of 45, then it is nothing but 1, 3, then 5, then it's not divisible by 10, it is divisible by 15, then 45. So the set of all divisors of 45 is a finite set, and we can consider the D45 together with the divisibility relation. Then this is a partially ordered set, and this is another example of a partially ordered set. Okay, now to represent a partially ordered set, we can we know that any relationship can be represented using a graph, but if it is a partial order relation, then it can be represented using a simpler graph, which is known as a hash diagram. And in hash diagram, we eliminate the steps which are obvious by the transitive relations and reflexive relation and symmetric relation. So, for example, let us consider a non-empty set S is equal to set A, B, C, and consider the power set of S, that is set A, set B, set C, then set AB, set AC, set BC, and set ABC, and the null set. And we can we can use a graphical representation to represent this subset of relation defined on the power set of S. And the relation can be represented using a graph like this. So the elements of P of S can be represented using dots. Here it is the null set, then A, B, C, then this is the set AB, is all our sets, then set BC, and set AC, you can put somewhere middle here, AC, then the total set ABC or X itself. Now, a relation is a subset of relation, and we know that phi is a subset of all other sets. So phi related to A, phi related to B, and phi related to C. Then phi related to AB, and phi related to AC. So there are so many edges like that. But observe one thing: this A is a subset of AB. And since the relation which we are discussing is a partial order relation, it is transitive, and since phi is a subset of A and A is a subset of AB, naturally phi is a subset of AB. So this edge from phi to AB is obviously given by the transitive relation, or is obvious from the transitive relation. So we can ignore the relations or the edges which are implied by the transitive property. So phi is a subset of B and B is a subset of BC. So phi is a subset of BC. That is obvious. So we can exclude that particular edge from phi to BC. And since AB is a subset of ABC, and phi is a subset of A and A is a subset of AB and AB is a subset of ABC, we can ignore the edge from phi to ABC. And in a similar way, since set A is a subset of AB and AB is a subset of ABC, we can ignore the edge from set A to set ABC. So we ignore all the edges which are implied by the transitive property, and we also ignore the edges which are implied by the reflexive property, and therefore we don't draw the edges from phi to phi itself. And so the resulting diagram is something like C is a subset of AC, and C is a subset of BC, is the set, and BC is a subset of ABC, AC is a subset of ABC, and right. Okay, and you don't need to draw the directed edges here, because here the relationship is from bottom element to top element. Phi is related to B and B is related to B is not related to AC. B is related to BC. So here like this, and B is related to AB. So here we have an edge. B is related to AB. B is related to BC. C is related to AC and BC. A is related to AC also. Okay. This is the minimum required edge to represent our relation, and the diagram hence obtained is known as Hayes diagram, and this is a simple method to represent a partial order relation when we have the underlying set is a finite set. If you have an infinite set, drawing a Hayes diagram is not the simplest way to represent a partial order relation. Now, next concept is totally ordered set. A partially ordered set is called a totally ordered set if any two elements in the partially ordered set is comparable, or in other words, if R is the relation defined on R, and if A and B are two elements from A, then either A is related to B or B is related to A. In that case, it is a totally ordered set or linearly ordered set, or in other words, it is also known as a chain. Set of all real numbers together with less than or equal to identity is a totally ordered set, because if you take any two real numbers x and y, either x is less than or equal to y or y is less than or equal to x. But if we consider the power set of S together with subset of relation, uh, is not a totally ordered set, because it's obvious here. Here, if we take two elements, set A and set C, set A and set C, set A is not a subset of set C, and set C is not a subset of set A. So the subset of relation is not a totally ordered total order relation, but the less than or equal to relation defined on the set of all real numbers is a totally ordered set. Now we are going to define some special elements in a partially ordered set. First one is maximal element, and second one is a minimal element. So just go through through the definition. An element x in A is called a maximal element if there exists no A in capital A such that x is related to A. So if we have a Hess diagram, a maximal element is an element x in such a way that no element in A is uh, there is no element in A such that x is related to A. So x is related means there is an edge from A from x to A. There is no element A such that x is related to A. So in other words, there is no element A which is placed above the element x in the corresponding Hess diagram. And minimal element is just the opposite. If y is a minimal element, then it is said to be a minimal element if there exists no x A belongs to capital A such that A is related to y. So if y is here, there is no A in A such that A is related to y. Such an A is not present. In that case, y is called a minimal element. If you think in terms of Hess diagrams, they are the elements in the bottom end, and it is not no element is related to that particular element. So if you consider a particular Hess diagram uh, like this, here elements A, B, C, D, E, and F. Then this F and E are maximal elements, and A and B are minimal elements, because there is no element in the set A is equal to A, B, C, D, E, F. Uh, there is no element in the set A which is related to A or B. So A and B are minimal elements. So minimal elements are A and B, and the maximal elements are F and E, or E and F, because there is no element which is on top of F and E. So F and E are maximal elements. So that's the concept of minimal elements and maximal elements. Now, uh, a particular partially ordered set may have a number of minimal elements and a number of maximal elements. In the case of okay, Now let us move on to the next definition. There's the greatest element and least element. The greatest element, uh, an element G is said to be a greatest element of a partially ordered set if for all A belongs to A, A is related to G. If we take any A from the set A, that A is related to G either directly or A is something in case diagram terms, A is something like can be something like this. Okay, anyhow, for any element which is taken from A is related to G. And in that case, G is called the greatest element, and an element L is called the least element if for any element A taken from capital A, L is related to A. L is related to any other element in the underlying set A. In that case, L is called least element. And the difference between minimal element and least element is that least element is unique, and a particular partially ordered set may have more than one minimal element. And if there is a unique minimal element in a partially ordered set, then it is a least element also. So a particular partially ordered set may or may not have least element, but a finite partially ordered set always possesses a maximal element and minimal element. Now, if you look at this particular phase diagram, the maximal element and minimal element are phi and set ABC. There is no element which is related to phi, so phi is the minimal element. Phi is a minimal element, and ABC is a maximal element. And in this particular case, there is only one minimal element, and that is our least element. And here there is only one maximal element, and that maximal element is the greatest element. Okay, so the greatest element is unique, least element is unique, and the maximal and minimal elements may not be unique. Now the next concept is upper bound and lower bound. A be a partially ordered set, then B is a subset of A. Not belongs to a subset of A. B is a subset of A. The upper bound and lower bound are different for any subsets of A. Then an element, say A belongs to capital A, is said to be an upper bound of B if for any element belongs to B, small b, say it is related to A. If all element of B is related to a particular element A, then A is called an upper bound. And say an element L belongs to A is a lower bound if L is related to all elements of B. In that case, B is called a lower bound. And if you consider a particular example, R together with less than or equal to identity, then consider a subset of R. R is the set of all real numbers can be denoted using our real number. Then consider the closed interval 0 1. Then any, say if we consider the lower bound, then an element is said to be a lower bound of the interval 0 1 if L is related to all the elements within the interval 0 1. So if we take an element here like minus 1 is less than 0, less than 1, and minus 1 is less than any other element in between 0 and 1. So minus 1 is a lower bound. Similarly, the case is with -2, -3, -4, etc. So there are infinitely many lower bounds. In a similar way, we can find the upper bounds. Like if you take 2, then 1 is related to 2, 0 is related to 2, or 0 less than 2, uh, zero point 0.5 is less than 2. So any element between 0 and 1 is less than 2, and there are 2 is an upper bound, and there are infinitely many other upper bounds like 3 or 4, or in between that we can have the number pi. All the numbers which are above 2 or 3 are upper bounds. So there are infinitely many upper bounds and infinitely many lower bounds, and we are not interested in uh, a property which is satisfied by infinitely many elements. So if we consider the least upper bound, there are infinitely many upper bounds. Then what about the least upper bounds? Or there are infinitely many lower bounds, and what about the greatest lower bound? So these are some special elements. So the least upper bound is, there are many upper bounds and the least one is 1. 1 is the least upper bound. Least upper bound is 1. And the greatest lower bound is obviously 0. So 0 and 1 are the least upper bound and greatest lower bound. We are interested in the least upper bound and greatest lower bound. Now, let us uh, go through uh, the common partially ordered sets and check whether what's the meaning of least upper bound and greatest lower bound. So if we consider the set of all real numbers to with less than or equal to identity, then uh, if we take two elements a and b, then uh, obviously either a less than or equal to b or b less than or equal to a. Then if we are looking for the upper bounds, then any element in the real number system which are greater than a and b are upper bounds. Then the least upper bound is nothing but the maximum among a and b. That's the least upper bound. And the greatest lower bound is nothing but the minimum among a and b. And if we consider the set of all subsets of S to with the subset of relation, then if we consider two elements from power set of S, then the least upper bound is nothing but A union B. So A is a subset of A union B and B is a subset of A union B, and there are many other sets for which A and B are subset of, but A union B is the least one. And in a similar way, the greatest lower bound is nothing but A intersection B. So A intersection B is a subset of A intersection B is a subset of B, and there can be many other sets like there's a phi. Phi is a subset of A and phi is a subset of B, but phi is also a subset of A intersection B. So A intersection B is the greatest lower bound in the case of power set of S to with subset of relation. Now, if you consider the set of all positive integers or any subset of it together with the divides relation, then we have two integers a and b, positive integers from Z plus, then the least upper bound is the LCM of A and B. So A divides LCM of A and B and B divides LCM of A and B. And there are many other numbers like AB for which A divides AB and B divides AB. But The LCM is the smallest such number. And if we are looking for the greatest lower bound, then it is nothing but the HCF or the GCD of A and B. The highest common factor or greatest common divisor of A and B. That's the greatest lower bound of two elements A and B. And this can be extended to any number of elements. If we have three real numbers, then LUB is the maximum of A, B, and C. And there's a problem if we consider a finite subset of R, then this definition can be extended. And if you have an infinite subset, that may make some problems. So anyhow, we are not going into that much details here. Just think about that in detail. Okay. And if we consider the subset of Z plus, there's one problem. If the LUB or GLB is the LCM of A and B or GCD of A and B, that's fine. But we have to check whether that particular element belongs to our underlying set or not. In the case of Z plus, that is obvious. Obviously, Z plus is the set of all positive integers, and the LCM and GCD are always positive integers, and that will belongs to Z plus. But if we take any subset of Z plus, uh, instead of just check whether the LCM or GCD belongs to that subset of Z plus or not. That is very much important. Anyhow, that's the concept of uh, greatest lower bound and least upper bound in the case of our familiar partially ordered sets. Now, the next definition is of lattice. A partially ordered set is called a lattice if the elements x and y, for any arbitrary elements x and y, uh, the LUB, least upper bound of x and y, and greatest lower bound of x and y both exist in A. In that case, it's called a lattice. So, for example, Z plus 12 with divides. If you take any two positive integers A and B, then there is an LCM and that belongs to Z plus. And if you take any two real numbers, it has HCF and that again belongs to Z plus, and therefore it's a lattice. So that's the concept of a lattice. If both LUB and GLB belongs to the underlying set, then it's known as a lattice. And we also make use of another terminology. If you have a least upper bound, is denoted by x or y and is known as our joint. And if you have greatest lower bound, that is denoted by x and y and is known as our meet. And a lattice can be defined as if there is a relation and if any pair of elements in A has a join and meet in A, then such a set is called a lattice. And that's an algebraic definition of lattice. Uh, we are not dealing with lattice here as structure which is generated from the partially ordered set. Here we deal the structure just as something axiomatically we consider it. So we define lattice as a lattice axiomatically here. We have a non-empty set L and two relations join and meet defined on it. Then it's called a lattice if it has the following properties. That is the commutative property A or B is equal to B or A. and A and B is equal to B and A. Associative properties like A or B or C is equal to A or B or C, and A and B and C is equal to A and B and C. Absorption clause like A or A and B is equal to A, A and A or B is equal to A. If these conditions are satisfied, then it's known as a lattice. Now, um, we can classify the lattices based on some of its properties. First one is bounded lattice. So, a lattice is said to be a bounded lattice if it has the greatest element and the least element. So, if we have a finite set, then there is a greatest element, and that greatest element is usually denoted by 1, and there is a least element which is denoted by 0, and the phase diagrams are like this. In between these 0 and 1, we have the phase diagram. Okay, so bounded lattice, if you consider the power set of a finite set together with the subset of relation, then it has a greatest element, which is S, and has a minimal element, which is phi, and therefore is a partially ordered set, which is a lattice, which is a bounded lattice. And if you consider the set of real numbers together with less than or equal to identity, then it is a bounded set. Sorry, it is a lattice, because for any two elements we can have the meet and join, but it's not a bounded lattice because it does not process any greatest element or any least element. And if we consider the set of all positive integers together with divides, then it has a minimal element which is 1, minimal element or least element 1, but there is no maximal element, and therefore it is not a bounded lattice. So that's the concept. If there is a least element and maximal element, then it becomes uh, least element and maximal element, then it's a bounded lattice. And remember one more thing: if you consider this less than or equal to relation on the closed interval 0 1, then it becomes a bounded lattice, because 0 is the least element and 1 is the maximal element. And now we can move on to the next definition, that's of complete lattice. A complete lattice is a lattice for which every subset of L has a greatest lower bound and least upper bound. In particular, a complete lattice has a greatest element and least element, and therefore it is a special case of bounded lattice. For a lattice, any two elements, any pair of elements has a GLB and LUB, and in a complete lattice, any subset of L should have a greatest element and least element. That's the difference. Now, sublattice, if L is a lattice and M is a subset of L, and if you restrict the relation of join and meet to the subset, then if the subset become a lattice, then it is called a sublattice. That's the concept of sublattice. So we have known this set L, which is a lattice with the join and meet. Then if you consider a subset of L, say M, and if you restrict these two relations to M, then, and if you consider this M together with this join and meet, then if it become a lattice, then it is known as a sublattice of the total one. So if you consider R together with less than or equal to identity is a lattice, Then if you consider the set of all integers together with less than or equal to identity, then it's also a lattice and it's a sublattice of R. So we can write Z less than or equal to is a sublattice of R less than or equal to. Now distributive lattice, if the lattice satisfies distributive laws and join and meet, then it's a distributive lattice. Now for distributive lattice, okay, simply this power set of S together with subset of relation is a distributive lattice because we know that the union and intersection are distributive under each other. So it's a distributive lattice. So in terms of abstract definition, it can be as P of S union intersection is a distributive lattice. Then I think that's enough for now, and that's all we have about partial order relations. So we start with partial order relations and develop to the concept of lattices, and in between them there is an important concept of Hayes diagrams, and the most important partial order relations we come across are less than or equal to subset of and divides, and the less than or equal to can be defined on the set of all real numbers and any subset of it. Subset of relation can be defined on the power set of any set and any subcollection of power set of S, and divides relation is defined on the set of all positive integers or the subsets of Z plus like D30, D45, D15 or D7 etc. That is devices of 30, devices of 45, devices of 15, devices of 7 etc. So that's all about this particular module, and thank you.